We are going to do this, okay, and for that we are going to first try to understand that where from exactly do we have this Fermi Dirac statistics, okay. So we're going to start with the idea of Fermi Dirac energy distribution law, okay, distribution law. So for that we have to consider a situation, okay, and this is something which will be interesting, and at least you will get it clearly. Suppose there is a school, okay, there is a school, and this school has got n number of classes, okay, so it might be 30 classes, 40 classes, whatever. There are n number of classes in this school, and it is divided like this, okay, and each of these classes has got, let's say, n members, let's say n1 students, okay, n1 students, n2 students, n3 students, n4 students, and so on. So if we just keep on doing it, we might get around, let's say, nk students, okay. So that means we are dividing this entire box into k cells. So there are classrooms, k classrooms, and there are n1 students in each block, and each of these classes has got, let's say, g number of benches, okay. So get the idea. This is not something which you are supposed to write in your exam, but for understanding this is very simple. G number of benches, and there are n1 number of students that needs to be arranged in this g number of benches, okay, and there are k such cells. So that means there are k rooms in which there are gi benches, and n1 student needs to be arranged. Now the situation is such that one student can sit in one bench. It may be a table chair system. One student can sit in one bench. So we obviously know that this gi will always be greater or equal to ni, okay. It cannot be obviously more. The number of students would always be less than the number of benches, or at least equal to the number of benches. So this is the idea of actually Fermi Dirac distribution law, and what happens is we basically are using it to understand the distribution of the indistinguishable particles. So even if objective questions are coming, you can definitely get your answers by using this idea. So indistinguishable particles, and these indistinguishable particles are actually following the Pauli's exclusion principle. This is Pauli's exclusion principle. Now the Pauli's exclusion principle obviously says that no two particles or quantum mechanical particles can occupy the same quantum state. They must have got different properties. If not, they cannot actually do it, okay. So for this, understanding this Fermi Dirac statistics, what we do is we are basically going to consider an isolated system. This is my isolated system, and it simply means that it is in thermodynamic equilibrium, okay. That means the particle and total number of particles, that means n, and energy, let's say E, are constants. So it might be that the energy will change. If that happens, then this system is not isolated. But if the energy does not change, the total number of particles does not change, we can actually consider it to be a isolated system. So as I said, if I consider just one classroom, in which, let's say, I want to arrange n1 number of students, okay, and what happens is there are g1 number of cells. This is actually called cells, or let's say g1 number of benches. So this is g1 number of cells, and this is number 1. This is number 1, so it will go up to k. So this is number k, this is number 1. So this is something which is being arranged, okay. So what we understand here is that we can say number of particles, that's the first thing. In our analogy, we can say the number of students. Then we can say what is the energy in each box, okay, in each cell, 1, 2, 3, and so on up to k cell. What is the energy in each, okay. And then we have got something which we can write it down as compartment number. So this is first compartment, second compartment, up to k compartment. Okay, so this is the idea that should be clear when we are actually talking about Fermi Dirac statistics, because that is also needed in the final formula. N1 maybe N2, and then there are a number of students or particles which will be nothing but Nk. Okay, energy for the first one may be epsilon 1, for the second one might be epsilon 2, and will go on, and finally it will be epsilon k. And then compartment number, it might be 1, it might be 2, and then we can actually have k compartments. Now each of these compartments will have cells. Okay, so as I said, each of these compartments, each of these classroom will have benches, and let's say these are called cells. So this is like, it will have G1 cells, and then it will go on, and this one will actually have GK cells. And based on this, we actually have the Fermi Dirac distribution. Okay, so let's just have a quick look on how we can actually do it. Okay, now the question is very important question, which will actually clarify things here. How can we arrange n1 particles? So that means n1 number of students, you can say, in GI space. That means in our analogy it is in GI number of benches, so in GI space. So that may be a very valid question, and for that what we can use is, we can use the idea of combination. If you remember, permutation and combination, very important tool in statistics, and we can actually use this logic of combination, and it says that we can have it like this: G1 C N1. Okay, N1. Okay, let's say we are writing it down as G1 space. Okay, so G1 C N1. So that's the space that we basically have. And if you remember, this is combination, so this would be nothing but factorial G1 divided by factorial N1 into factorial G1 minus N1. There will be G1 minus N1, and obviously we know that G1 is greater than N1, number of benches is greater than N1. Okay, so it is G1 on top and N1 at the bottom. So this is the basic result that we have. Okay, now this is the case only for one particular classroom, and there are k number of classroom. That means what will be the total combination? We have to multiply all these parameters. Okay, and this comes in with the calculation. So now what we are going to do is, we are going to find out the total probability. Okay, so for this, let me just write down the heading for this. This is your thermodynamic probability for macro state. And we have got how many states here? We have got N1, N2, and so on. It's Nk. So these are the number of particles that are there, and for this probability we usually denote it by W. That's a standard notation, and we can write it down for the first classroom. It is G1 C N1 into G2 C N2 into, and so on. It's GK C Nk. So I hope you got this. This is actually all basic probability, and then what we can do is, we can expand it. So expansion means factorial G1 by factorial N1 into factorial G1 minus N1, and then similarly we can do it for G2. Let me not take this, let me write down the final result. Here the last one would be Gk divided by factorial Nk into factorial of Gk minus Nk. So that's the total number of combination that we have. Now you see, all of them are multiplied here. Okay, and it is 1 1 1 1, and then 2 2 2 2, then it will be k k k k, and so on. But all these are multiplied, these are not added. So if it is multiplied, we don't use the summation sign, we use this symbol, which is pi, and this symbol will actually be talking about the multiplication term. So I is equal to 1 to k. So please remember this notation. Whenever we write down summation, we are talking about the additions, and whenever we are writing it down in terms of pi, we are talking about the multiplication. So all these are getting multiplied, so I can simply write it down as factorial Gi divided by factorial Ni into factorial of gi minus ni, and of course I goes from 1, starts from 1, goes to k, so it's I is equal to 1 to k. So this is important. Okay, now what we have to do is we can actually try simplifying this. Okay, and for that, first thing we can do is we can take the log on both sides. Okay, so if you recall the log property, there are certain log properties which are important. I hope you know it. If I take log of a into b, this would be nothing but log of a plus log of b, and if I take log of a by b, this would be log of a minus log of b. So that means I can take the log on both sides, so I can simply write it down as log of w. All these terms are actually getting multiplied, and whenever I am taking a log, the multiplication of two terms will actually become positive, so it will become plus, sorry, not positive, plus. I'll keep on adding, so that means this multiplication can be replaced by summation because we are taking a log term here. So we can use the property of log to simplify things. This is 1 to k, and then I can take this log of this gi. So if I just put a bracket, this is on top, so I'll just simply write it down as log of factorial gi. This is the bottom that is divided by, so to divide it by we'll take minus log of factorial ni minus log of factorial gi minus ni. Okay, that is also at the bottom, so we can actually take the division symbol, and that's it. Now what we do is we are actually going to simplify things. Now it's not very complicated, but you have to know a rule. I think this is something which you always use in statistical mechanics, so if you don't recall that, let me just write it down. This is something which is called Stirling approximation. It doesn't have a derivation for it, but we are not going to do it. We are just going to use the result here. Stirling approximation. It talks about the log of a Stirling approximation. Stirling approximation, it actually talks about the log of a factorial quantity. So if I take Stirling approximation, I can simply write it down as log of n factorial, okay, is equal to n log of n minus n. So this is my Stirling approximation. I am not going to do this in detail because this log of gi, you can actually write it down as gi log gi minus gi. Similarly, log ni, you can write down ni log ni minus ni, and log gi minus ni, you can write it down as gi minus ni log of gi minus ni minus gi minus ni. Okay, you can do that, and then what you can do is you can actually open the bracket, and when you do all these things, the final result that you are going to get, it's just two lines that I am skipping here because I think you can do it. It's very simple. 1 to k, that will remain the same. The first term would be there, gi log of gi. When you open this, you will get a minus gi term. You also get a minus plus gi term here because you will get it when you open the bracket, because there is one minus here and there is one minus here to become plus, so that term will actually get cancelled out. Okay, so you can just simplify this. I'm leaving it to you, and then you can write it down as ni log of ni, that will be your second term. The third term would be gi minus ni into log of gi minus ni. So this is the term that you are going to get when you are going to use the Stirling approximation. Okay, now when we are talking about the probability, we actually want to find out the maxima. Okay, maxima, that means what is the maximum probability. Now as I said, we are talking about the thermodynamic probability for microstate, and we want to find out the maximum probability. That means what we do is we actually use the property or a tool in maths where we differentiate this term and equate it with 0 to find out the maxima. Okay, so for maxima, what we can do is we can write down this. For maxima, what we do is we should see that for maxima in general, we know that d of a term must be equal to 0, differentiation. So I can take it ddx of this should be equal to 0, whatever may be the function. So here also the same thing. If we differentiate this, we should get, even if fx is 0, fx means it's a function, so obviously we can take log of that, that will also be equated to 0. So we can simply write it down as log of w is equal to summation I is equal to 1 to k, and then I will take the d of whatever term we got and then equate this to 0. Okay, that is what we have to do. And you know, again I'm not doing it because I think it will take too much time, but I hope it's clear to you. Suppose you want to differentiate this, and we are differentiating it with respect to n, because gi is something which is fixed, ni is the number of particles, so gi is something which is fixed. So if I just write down the first step, here you will get summation I is equal to 1 to k, d of gi, that part would be 0, minus, and then let me just put a bracket here, get back to the previous page and check this. This is ni log ni, so that means I have to differentiate this, keep this constant, then I have to differentiate this and keep this outside. So let's do it. Let's take this second, this is the first function, so dd ni of d of log ni. Okay, so that means if I do something like this, d of ni log ni, so if I do it, I have to do it like this, ni d of log of ni property plus log of ni d ni. So this is something which I have to do. So here if I want to differentiate this, I have to, you know, ni, then I have to take d ni of log of ni, but there was no dni, so I'll just multiply it with dni plus log ni dni. Okay, so if we do that, this is 1 by n, ddn of log n is 1 by n, so I'll take ni into 1 by ni into dni plus log of ni dni. So this ni and I will get cancelled, I'll just get dni. So here what happens is, if I simplify this, I can write it down as dni plus because I have taken the minus and I have put a bracket there, plus log of ni dni. Okay, so I have just shown it for one, you can check this, this is the first one, and then you can similarly do it for this also. Okay, and then you can actually simplify this. Okay, and after simplification, when we actually equate it with 0, this is something which I leave it to you, because you know there's so many things to do, so I leave it to you. But when you do it and you actually simplify it, you get this term. Okay, and let me write down this term here. You get this term, this must be equal to 0, so let me directly write it down as equal to 0, because that's the condition for finding out the maxima. The term that you should get is this, I is equal to 1 to k. You have to do it carefully and slowly so that you are getting your answer, log, and then gi minus ni divided by ni, close the bracket, d of ni. So this is the term that you are actually going to get. Okay, in a similar way you are going to get two more terms. You know, the number of particle is constant, we said, as n, which is equal to, you know, total number of particles. That means I'll take n1 plus n2 plus n3 and add them up, so that is ni is equal to constant, is equal to constant. So I can simply say that you know, this summation I is equal to 1 to k n I. If I take the differentiation of that, that has to be 0, obviously that has to be 0, because this side it's a constant, I am taking d of that side. What we can do is we can actually multiply both sides by alpha, because depending on the condition we might need to have a constant change. So this is multiplied by alpha on both sides, I'll get alpha dni is equal to 0. So this is one term that we can actually consider. Okay, so let's take this as a, let's mark this as a, let's mark this as b. Okay, and then what we can have is one more term. We want to find out the total energy, that's again simple. If we write it down as u, n1 particles, n1 number of particle has got energy u1, and n2 number of particle has got energy u2, and so on, and finally nk number of particle has got energy uk. So in that way I know that what is the total energy of the system. N1 particle has got u1 energy, n2 particle has got u2 energy, and I'll keep on adding them up and I'll get this result. So that means again here also I can use the summation I is equal to 1 to k, and this would be nothing but ni ui. Okay, here also what we can do is we can differentiate this and check, because this total energy of the system will again remain constant. Why? Because we said that this is actually an isolated system. So that means this total energy will again remain constant, and what we can do now is we can again differentiate this and we can get this result something like this. Summation I is equal to 1 to k into ni dui is equal to 0, because that side we actually have a constant. Okay, and let's multiply this also on both sides by beta, just a constant, and beta is equal to 1 by kt. We are using that term because it has something to do with the Boltzmann constant. So beta ni dui is equal to 0. Let's mark this as c, and this beta is equal to 1 divided by kt. So we have got these three terms. This is a, that is b, and then c. And what we can do is, now almost we are at the final step. What we do is we take a, subtract it from subtract b from it, and then also subtract c from it, because for all these equation one side is 0, this side is 0, this is also 0, and this is also 0. So we can subtract one from the other and LHS will remain the same as RHS. Okay, and what you do is now you subtract one from the other, use the properties of log, and what you get is this result: ni divided by gi is equal to 1 divided by 1 plus e to the power alpha plus beta ui. Okay, where beta is equal to 1 by k. This is Fermi Dirac distribution law. Let me tell you, this is actually a very long topic. If I derive this all steps, it will take minimum of half an hour more. So I'm not doing it, but then this is very simple, because I already told you how to do it. You do your adjustments properly, and then you should be able to get this result. Okay, this should be more or less there. Okay, so what we have now is the Fermi Dirac distribution law. Based on this, we can say the probability of the existence, okay, of a particle in a particular energy level. But the question is how we can actually do it. Okay, there are some sums as well which is actually based on this particular formula. Okay, the first thing, I hope it's clear. Yesterday also we have discussed in the last class what is Fermi energy. So at 0 degree Kelvin, it's minus 273.15, a very low temperature. It is assumed that there will be definitely some electrons which will have some kind of energy involved, and that energy that we actually have, based on that we can say there is a level. What is the energy? Let's say some EV, and that particular level is actually called the Fermi energy or the Fermi level. Okay, Fermi energy level or Fermi level, and the energy of that level is called obviously the Fermi energy. And it is said that obviously above this there are no electrons, but below this there will be an existence of electron. So if you consider the energy of the Fermi level as epsilon f, and there isn't any energy level epsilon below it, okay, then the chances are that definitely there will be an electron which is there in this level below. But if there is an energy level, let's say epsilon dash above the Fermi level, we for sure know that the probability of existence of an electron is 0 in this case. And if it is below the Fermi level, for sure we know that the probability of the existence of the electron is 1. Okay, so this is a very important thing. This is also a statement that we are going to use later. So let's do it. Okay, but before that, what we are going to do is we are going to derive something which is actually called the Fermi Dirac law of distribution, the same thing which we already have said, but this time it is not in the general case, it's basically for the energy of free electrons, of energy of free electrons, okay, in metals. So it's a long topic, but I hope you get the gist. This is very important, okay. Whatever distribution law we have just now seen, we are going to actually use it to find out this in metals, okay. So let's try doing this, okay. So when we talk about energy, we know the number of particles, right? We have already said that in the previous derivation, okay. This is the number of particles, and let's write it down again. We can simply write it down as Ni divided by Gi is equal to 1 divided by 1 plus e to the power alpha plus beta, so that's 1 by kT into the energy, okay. So energy we have denoted it by U, so let me keep it as U, or you can write it down as E also, okay. Let me write it down as U only. Let me just keep it consistent, Ui, okay. So that means Ni is equal to Gi, where G is the subcells or the cells which we have, e to the power alpha plus 1 divided by kT into Ui. So this is my statement here, but now we are saying we are going to find out the distribution of energy of free electrons. That means we are not concerned about the number of particles, but we are considering now the energy, and we know that the number of particles is actually directly an energy dependent factor, so we can write it down as a function of U, energy, and then I can multiply it with U, because if I want to find out the total energy, I know N1 particle will have epsilon 1 energy, or U1 energy, sorry, N2 particle will have U2 energy, and so on. So in this state, how many and what is the energy? N1, U1. So if you are basically considering a small value, it is du, right? Definitely we are going to take help of maths to find out the total energy, but that's later. So then that means G also, it is going to be a function of energy into du. So this is the start that we need. This is from where we are going to start our derivation for this. So let me mark this as expression A, okay, and let's use some logic, okay. Let's use some logic. At T is equal to 0 Kelvin, okay, let's say there is an energy level U which is above the Fermi level, okay, and we know that if an energy level is above the Fermi level, no particle will exist. So I can simply write it down, no particle exists. This is something which we have already understood from this. That means we can say, therefore this term Nu by Gu or Ni by Gi, whatever, Nu by Gu has to be 0, quite obvious, okay, because there is no particle which will exist above this. This is giving me a probabilistic idea, giving me the number of particles. There will not be any number of particles, because that comes from the definition, okay. But then if this U is less than UF or UF is greater than U, I know that there is definitely going to be a particle. That's mine. We can write down this Nu divided by Gu as 1, because by definition we know if the energy is below the Fermi level, there is going to be a particle, there is going to be an electron, okay. So this concept of Nu divided by Gu, which tells me whether a particle exists or not in an energy level, is actually called occupation index. This is a very important technical term. This is called occupation index. So you never know, there might be some trick questions on occupation index, and this might be a good way to know it. So this is Nu by Gu, which is actually called the occupation index, okay. At the same time, if U is equal to UF, then also we know that there will be electrons at the Fermi level, so there also this occupation index will be 1, okay. So therefore what we can say is, therefore for U is equal to uf, that means we are talking about the exact Fermi level. This expression A that we have, okay, this expression A, nu by gu, we can take it here, okay. We know that will actually become equal to 1, okay. This will actually become equal to 1, so you can check it. This is 1, this would be equal to 1 divided by, this is alpha plus 1 by kt, so we can actually, you know, take it like this. So it will be 1 plus e to the power alpha plus u f, because we are saying u and uf are equal, so we are talking about the Fermi level, uf divided by kt. So we can take it like this, and then there is a 1 plus. Now what you can do is you can, you know, simplify this, you can cross multiply, there will be a 1 on both sides, so it will become 0, and if you do that, you will get it u to the power alpha plus uf divided by kt is equal to 0, okay. What we can do is we can take the log of this, and if you take the log of this is natural logarithm, log of u will become 1, and this is to the power, if you remember this result, log of e to the power x will be nothing but x, this x will come in front, and log of e to the base e is 1. So if you do that natural logarithm, we are going to get this result as alpha plus uf by kt is equal to 0. So from this we can find out what is my alpha, which was actually an unknown. It is nothing but uf divided by kt. So this constant alpha we have actually found out in terms of kt. So it is minus of uf divided by kt. Okay, don't worry, I'm going to provide you the notes for this. If you understand these steps, I think easily you can read it directly from the notes. Okay, so that will help you out. So alpha is this, we need to use alpha here because we don't know what is this, so we can actually put down the result directly here in A. Okay, so if we do that, what we can say is, let's take a new page. Therefore A implies, what was our A? Our A was, and you, just like in quantum mechanics we are using conditions to derive unknown, here also we are going to do the same. Sorry, not gu, that's not gu, that's du is equal to, this is gu du, and at the bottom it's 1 plus e to the power alpha, but alpha we have just now found out is nothing but uf by kt. Okay, if we go back, check, this is minus uf by kt, this is alpha plus ui by kt. So ui is the energy of that particular state, so it is minus uf by kt plus ui by kt. So what we can do is we can simply write it down as gu du divided by 1 plus e to the power u minus uf divided by kt. This is my result. Okay, now the other thing that we don't know is gu du. Okay, what is this gu du? That means what is the number of cells if we are basically considering a phase space. Okay, that will obviously depend on the density, but you know, I'm not going to derive this again because this is going to be completely different, so we are not going to do it. This is again a concept in statistical mechanics which is called phase space. Okay, so the number of phase space, the sad part is you have to remember certain things, and this is one of the results that you should remember. Number of phase space cell, if I told you, you remember what is g. G is the number of benches in the class, or that was the analogy, and that means that g is actually representing the cell. So number of phase space cell, okay, and it will obviously depend on the velocity, okay, that how many cells are there, because it's energy dependent factor. Cell in the momentum range, p plus dp, p and p2, let me write it down, 2 p plus dp. Okay, So how many are there? There is a very standard result for this. You can simply write it down as Gp dp is equal to 4 by v p square by h cubed. H is volume here, we are talking about height, it's a cubical space, so it's a cube we are saying, assuming it's a cube, this is volume. Okay, this is the result that we are going to actually use, but you know this is gu du and not gp dp, so we have to write down all the terms in terms of u, and u we know is nothing but the energy, and we simply know that what is my u and p relation, that momentum is equal to 2m into energy. So energy I am denoting it by u, so let me not change the notation right now. And if we differentiate both sides, this side would be nothing but d of p square would be nothing but 2p dp, okay, and this side it would be nothing but du, so 2m is a constant and du, so this 2 and this 2 will actually get cancelled, and what we have here is p dp, or we can write it down as dp. dp is equal to m du divided by p. So this is the result, but p is root over 2mu, so I can write down all the terms in terms of du divided by root over 2mu. So this is the result that actually I can use, okay, and I can replace this result in gu du, okay, and in gu du if I replace it, okay, this again is something which I'd like to leave it to you, okay. This one again you can simplify further, you can simply write it down as m by root m, so it will be root m on top, and at the bottom it will be root over of 2u, and there will be a du. So what I can write down in place of dp is this, and what I can write down in place of p square is 2mu, okay, and then if I just simplify this, the final result that I am going to get is gu du is equal to 4, or I will get an 8, I think, yeah, I will get an 8 here, 8 by v divided by h cubed into root 2 m to the power 3 by 2 into u to the power half d cube. So see, what I am doing is I am writing down this result which I should know, and then I can take p in terms of u, find out dp and replace it here. We are going to get everything in terms of u, so I can write down that g is a function of u du, okay, so I can simply write down this result. So this is what is important here, okay, and once I get this gu du, what I can do is I can replace it here, gu du, and I can get my answer, okay, that's simple. So that means this is actually a very important result, because I told you that what is the connection of energy. So nu du is equal to this result that we have, 8, we have to make a note of this, 8 by v divided by h cube, that is my gu du into root 2 m to the power 3 by 2 into u to the power half. In your tutorials also they are using this result, and I think in one place it was asked also, so I think it's important, 1 plus e to the power u minus uf divided by kt. Okay, so what is this? This is the Fermi Dirac distribution law of, let's write down, electron in metals.